welcome back to another video. Here we're going to be talking about the fundamental theorem of calculus. Anytime anything in math has the word fundamental, you know it's important. So, this is perhaps the most important video of the course. Let's start with a quick recap of last video. Last time, we introduced this thing called the definite integral. Right, so this would be the definite integral from a to b of f of x dx, and it was really complicated. It had this whole Riemann sum definition, yada yada yada. But really, there are just two things to know, at least for the purposes of this class. Number one, it measures net area under the curve. And I put under in quotes because under means just closer to the x-axis. Our picture for that is it measures this thing, subtracting away any sort of negative area. So that's the first thing to know about the Riemann integral. And the second big thing to remember is one quick criterion on what functions are integrable. Any continuous function on a to b is integrable on a to b. Alright, so those are the two big things. If you get nothing else from last video, here's what you need to know. Definite integral measures net area under the graph of f of x, and which functions are Riemann integrable? More than this, but ones that are for sure integrable are anything that is continuous. Alright, so now what we're going to do is we're going to connect definite integrals which they measure this thing that we want, but they're hard, with derivatives and indefinite integrals. Which are easy in comparison. At least we kind of have a handle on how to compute those. And so our big bridge is going to be called the fundamental theorem of calculus. Which I guess I can just leave this up here. This will be the fundamental theorem of calculus, which I will sometimes abbreviate as FTOC. The theorem states, let f of x be a Riemann integrable function. So, any continuous function automatically works. There are Riemann integrable functions that are not continuous. Case in point, something like that would end up being Riemann integrable, and we'll state that later. But there are discontinuous Riemann integrable functions. Anyways, anytime you have a Riemann integrable function on your interval a to b, we're going to let capital F of x be any antiderivative of little f of x. So what does that mean? That means capital F prime of x is equal to little f of x. Okay, anytime we have this setup, we have a function that's integrable, and we have an antiderivative of it. Then, the definite integral from a to b of f of x dx is capital F of b minus capital F of a. And let me introduce a piece of notation, and then we'll talk a little more about what this means. Very common piece of notation is that capital F of x, and then we put a little bar, AB, is equal to f of b minus f of a. So, expressing our theorem in this notation, we have that the integral from a to b of f of x dx is equal to capital F of x going from a to b. Alright, so what impact does this have for definite integrals? Why do we care about this theorem? Because this theorem alone is what's going to make definite integrals a workable thing to compute. Why? Because we know how to find antiderivatives. We know how to find those. We get those from the indefinite integral of f of x, of little f of x. And we know how to find indefinite integrals pretty easily. So now, once we have any antiderivative of it, now it's just a simple numerical computation here with the antiderivative. This is easy. This is an easy thing to compute. And that is, in fact, equal to this whole complicated definite integral thing. This whole big infinite sum weird thing going on is just equal to this simple piece of subtraction. Fundamental theorem of calculus. Developed independently by both Newton and Leibniz, and they fought each other bitterly for the rest of their lives over getting credit for this. In fact, the debate still rages on today. But Leibniz did it. Anyways, so how do we use this in practice? Well, let's compute our very first definite integral. Let's compute the integral from 1 to 3 of x dx. Okay, well, I can choose any antiderivative I want by this theorem. So let's pick the general one for now, and then we'll see that there's a kind of unique choice that makes sense to make. Well, this integral, by the fundamental theorem of calculus, is equal to 1/2 x squared plus c from 1 to 3, because this is this is an antiderivative of x, and we evaluate from 1 to 3. Or in other words, we have 1/2 times 3 squared plus c minus 1/2 times 1 squared plus c. That's 9/2 plus c minus 1/2 minus c. Or in other words, 8/2. Because those c's cancel out with each other. And we'll notice that no matter what we chose c to be, these would cancel out with each other. So we might as well just always choose c is equal to 0. To simplify computations. unless you're told not to for some other reason. But even if you're told not to, it'll also just cancel out. So it'd be really weird for someone to tell you not to do that. And that's it. This whole big, scary infinite sum thing, which even for a function as simple as x, if you do it out by hand from the definition, this takes about half a page of work for me, knowing perfectly well what I'm doing. Not worth it for anybody. So, and when I say half a page of work, I mean like my personal handwriting, not my like solutions handwriting. But with the fundamental theorem of calculus, just a few lines. Nothing complicated happened there. With the one exception being actually taking this antiderivative, but we're already masters of that, at least in the case of something as simple as x. So, let's do a couple more examples. Let's find the area under the graph of f of x equal to x cubed between x equals 2 and x equals 6. So our picture for that, we have x cubed, which looks roughly like this. And we're saying, okay, between 2 and 6, please note that this graph is very much not scale. I want you to find this area. Well, that's just a definite integral. Can't be computed geometrically, no matter how hard you try. But with the definite integral, nice and simple. So we say this will be the integral from 2 to 6 of x cubed dx. Fundamental theorem of calculus says this is any antiderivative of x cubed. We'll choose x to the 4th over 4 between 2 and 6. Using our piece of notation, this is 6 to the 4th power divided by 4 minus 2 to the 4th power divided by 4. And I didn't bother to work this out ahead of time. I'm regretting that decision now. 6 times 6 is 36, times 6 is 216, times 6 is 1,200, 1,260 plus 36, 1,296. Divided by 4 minus 16. Or 4, what is that? That is 324 minus 4. 324. Nice. Well, we're 100 off for that, but still nice. So this whole nasty problem gets handled in just 2 lines by the fundamental theorem of calculus. Let's do another example. Find the area under the graph of f of x equal to x squared plus 4 between -3 and +2. And you might say, okay, does tossing a negative number in as one of our endpoints change anything? Not in the slightest. As long as the function is non-negative, it's truly the area under the curve. So our graph in this case, x squared plus 4 will look something like that. And we're going between -3 and +2. So yes, this is asymmetrical, that's on purpose. We're trying to find this area right there. And all it is, it's another definite integral. It's going to be the integral from -3 to 2. So moving left to right, -3 to 2. Of x squared plus 4 dx. Okay? Applying all our indefinite integral rules, that tells us that's x cubed over 3 plus 4x going between -3 and 2. And now it's just plugging in and juggling. So this is 2 cubed over 3 minus 4 times 2 minus -3 cubed over 3 plus 4 times -3. So, this is the other area of the kind of biggest mistakes people can make in calculus. Just sign errors, doing stuff like this. Don't let it happen to you. Just be patient, don't rush it. Make sure you plug each thing in, keeping the proper sign each time, like I nearly did right there. So, always double check your work, kids. Okay, this is 8 divided by 3 plus 8. And here we have minus, this is -27 over 3 minus -12. Yeah, you can still see that there. 8/3 plus 27/3 is 35/3 plus 8 plus 12 is plus 20. And if you wanted to merge it all into one single number, you get 95 divided by 3. 95 over 3, what? What units? Technically there are none. We're working in math world where there are no units. But I could slap units onto this curve as soon as I wanted. If I said this curve was measuring something in feet, then this would have area of feet squared. Simple as that. Alright, let's do a little bit more practice, and then we'll talk about how this gets applied to the real world. We'll do a couple examples of that. Let's evaluate the integral from 1 to 4 of 2x cubed minus e to the 2x dx, and the integral from 2 to 4 of 1 over x plus 1 over x cubed dx. Alright, well, let's do it. Well, to evaluate a definite integral, we need to first evaluate the indefinite integral. Let's split it up and do that. This is equal to the integral. Technically, I haven't discussed how to do that. Let's not worry too much about it right now. Let's just, you know what, let's do it. I'm going to tell you guys the sum rule and everything like that still work when it comes to definite integrals. We'll state that more formally later, but it does work. So for the sake of this problem, let's split it up. 1 to 4 of 2x cubed minus dx minus the integral from 1 to 4 of e to the 2x dx. It's 2 times the integral from 1 to 4 of x cubed dx minus, let's view this as 1/2 times the integral from 1 to 4 of 2 e to the 2x dx. Good exercise to make sure you understand u subs properly here. This will become 2 times x to the 4th over 4, evaluated from 1 to 4, minus 1/2 times e to the 2x, being evaluated from 1 to 4. Alright, so let's plug in our numbers and jump. This is 2 times 4 to the 4th over 4 minus 1 to the 4th over 4. And that's all minus 1/2 times e to the 8 minus e squared. Alright? Well, 4 to the 4th divided by 4 is just 4 cubed, which is 64. So we have 64 minus 1/4 minus 1/2 times e to the 8th minus e squared. These can't actually play together nicely. Doesn't work. So this becomes 128 minus 1/2, which is 255 divided by 2 minus e to the 8th minus e squared divided by 2. If you want to do, you could put a plus and then flop those around. Still will be minus there. Okay, that's our final answer. Doesn't need to be a nice number, but it's still just a number. Nifty, because trying to calculate that any other way would end in abysmal failure. But again, fundamental theorem of calculus makes it nice and simple. Let's do our other example. The integral from 2 to 4 of 1 over x plus 1 over x cubed dx. Integral from 2 to 4 of 1 over x dx plus the integral from 2 to 4 of 1 over x cubed dx. Let's rewrite that real fast as x to the negative 3rd power. Now, natural log rule tells us that this is the natural log of the absolute value of x, going from 2 to 4, plus, let's see here, power rule here says this will be negative 1/2. So, in other words, 1 over negative 2, x to the negative 2nd, from 2 to 4. Rewriting this, that's the natural log of the absolute value of x going from 2 to 4, plus negative 1 over 2x squared. 2 to 4. Moving up to here, that's the natural log of the absolute value of 4 minus the natural log of the absolute value of 2 plus negative 1 over 2 times 4 squared minus negative 1 over 2 times 2 squared. You'll notice I'm being very careful to keep all of my minuses. We have a minus here, and that's that minus, but going between 2 and 4 says, oh, plug it in at 4, and then subtract away the 1, 2. So be very careful when you're keeping track of all these. Move slow. Remember, writing your parentheses is going to be your best friend here because it'll keep you from messing things up. Okay, natural log of the absolute value of 4 is the natural log of 4. But even better, 4 is 2 squared. So then the natural log of the absolute value of 4, which is just the natural log of 4, is the natural log of 2 squared, which by natural log rules is 2 times the natural log of 2. So really we have 2 times the natural log of 2 minus the natural log of 2. Excuse me. So we're just left with natural log of 2 there, plus negative 1 over 2 times 16 is 32, plus 1 over 8. Doing some fraction math real fast gets you natural log of 2 plus 3 divided by 32. And that's your final definite interval there. So that's nifty. Now, how do we use all of this in the real world? Ostensibly the thing we care about. Alright, so our real world application of this. Suppose capital F is some function of interest. Maybe F measures the profit of your company. Maybe F measures the amount of time traveling somewhere takes, right? Maybe F measures just any sort of important quantity. The net change, I think we defined this in this course, the net change of F between A and B is f of b minus f of a. The ending value minus the starting value. That's how much f changed between a and b. It's just final minus initial. But the fundamental theorem of calculus says, hey, that's equal to the integral of a to b of f prime of x dx. So why do we care about this? Let's say we don't have information about capital F, right? Because this is nice and easy algebra. But if we don't have a formula for F, and I'd still very much like to know that thing, if we have info about capital F prime of x, or just capital prime, right? So let's say I don't know cost, but I know marginal cost. I don't know profit, but I know marginal profit. Maybe I don't know velocity, but I do know acceleration, right? If I have information about f prime, but not about f, the fundamental theorem of calculus lets us get what we want. You might say, but doesn't that mean I have to compute this in nasty Riemann subworld? Yes, asterisk. People have put a lot of work into figuring out ways to make this whole process simpler, even if you don't have an antiderivative handy. There's a lot of neat tips and tricks for that, some of which we'll explore, some of which we won't. And then there's other things that can happen where you can do basically numerical approximation using stuff like Monte Carlo methods, Runge-Kutta. There's a bunch of numerical methods that computers can run that compute this without actually doing the whole thing. So, pretty nice. Basically, it's easier to get this than you might think, and now the fundamental theorem of calculus gives us useful information about the function we want. Even if no analytic method is actually possible. Of course, in this course, analytic methods will always be possible, because it wouldn't be a good first course if it wasn't. Alright, so let's do 2 examples of the real world stuff, and then we'll call it. Suppose a population is growing at a rate of R of t equal to 200,000 t squared minus 150,000 t plus 456,789 people per decade. Where t is decades after 1980, like the year. So you have some population and you know it's growing, you know the rate it's growing at, but you don't know an actual function for that population. Okay, well, what do we want to know? What was the net population change from 1990 to 2010? So, here we have a situation where we know the rate, we don't know the actual function, but taking an indefinite integral is going to give us, essentially, a population function, which we can then use. There goes my chalk. And this is probably valid here. This is important stuff. Alright, so the net population change the thing we want is the integral from 1 to 2 of R of t dt. And you might say, well, why 1 to 2? Because t is decades after 1980. So 1990 is 1 decade, or sorry, not 1 to 2. 1 to 3. 1990 is 1 decade after 1980. 2010 is 3 decades after 1980. So we get the integral from 1 to 3 of r of t dt. All right, let's compute that integral. We have 200,000 t squared. So just using our scalar multiple rules and our sum rules, this is 200,000 times the integral from 1 to 3 of t squared dt minus 150,000 t. This will be 150,000 times the integral from 1 to t of 1 to 3 of t dt plus the integral from 1 to 3 of 456,789. So just using our sum rule and our scalar multiple rule to pull those things out. It's also possible to leave them in and use the use of. Take your pick. Does not matter. Well, if we start trying to compute those integrals, I guess I have a little more space down there. T squared is t cubed over 3 for the integral. So we have 200,000 times t cubed over 3 between 1 and 3 minus 150,000 times t squared over 2 between 1 and 3 plus 456,789 t from 1 to 3. All right, so that's 200,000 times 27 thirds minus 1/3 minus 150,000 times 8 halves minus 1/2 plus 456,789 times 3 minus 456,789 times 1. All right, start computing. 200,000 times 26 divided by 3 minus 26 divided by 3, 150,000 times 8 minus 1 is 7 divided by 2 plus something times 3 minus something times 1 is something times 2. And if you want, you can get a calculator out and go from there. I don't have one on me. But for the love of God, don't round. So many people made rounding mistakes on the midterm. And it just didn't need to be that way. Okay, let's do another example. Suppose a product's marginal cost function is given by f of x equal to 0.0003 x cubed minus 0.004 x squared plus 0.01 x plus 4. Okay, so that's your marginal cost function. The cost to produce the x plus first unit is that. Additionally, we are told it costs $200 to merely keep the factory running. Two questions. Question one, what was the total cost of producing the first 50 units of the product? Sorry, I had to dart there for a second. And when I say what is the total cost of producing this, I mean how much did it take to just produce those 50 units, irrespective of running costs of the factory. Second question, how about the 21st through 40th units? All right, so let's phrase these questions in the language of a definite integral, or two. Let's say our overall cost function has the name capital C of x. What's the relationship between marginal cost function and total cost function? Well, anytime we're talking economics, the word marginal means derivative, so we know that capital C prime of x is equal to little f of x. Okay, for the first question, we want C of 50. Cost of producing the first 50 units. How do we get it? Well, here's what we're going to do. I know that C of 50 minus C of 0 is equal to the integral from 0 to 50 of f of x dx. Why do I know that? By the fundamental theorem of calculus. C prime of x is little f of x, so this whole thing is valid. This is what we want, and we're told C of 0. C of 0 is 200. Right? The cost of making 0 units is, well, C of 0. Okay. So how do we compute this? Well, let's find this integral. This tells us that C of 50 minus C of 0 is the integral from 0 to 50 of just substituting in for f of x and splitting it up. We have 0.1234, or 3 integral from 0 to 50 x cubed minus 0.004 integral from 0 to 50 of x squared dx plus 0.01 times the integral from 0 to 50 of x dx plus the integral from 0 to 50 of 4 dx. All right. So, if we start computing all of these integrals, that's 0.0003 times x to the 4th over 4 between 0 and 50 minus 0.004 times x cubed over 3 between 0 and 50 plus 0.01 times x squared over 2 between 0 and 50 plus 4x between 0 and 50. All right. So where do we go from here? Well, we're just going to plug in our numbers. And we're still finding c of 0, or c of 50 minus c of 0. If we plug in 0 to any of these, they all have a factor of x, so those will just drop. Which means we're only really left with computing the 50s. So it's going to be 0.0003 times 50 to the 4th over 4 minus 0 minus 0.004 times, let's see here, 50 cubed over 3 minus 0, right? Because if we plug 0 in, x, that just drops. Plus 0.01 times 50 squared over 2 minus 0 plus 4 times 50. All right. Start running all of these computations. What do we get? Well, 0.0003 times 50 to the 4th divided by 4 was 50 to the 4th. 5 to the 4th is 625. And then I'm adding on 1, 2, 3, 4. So we have 625,000 divided by 4. Well, divided by 2 would be 312. Right? 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Perfect. Alright, so that's divided by 2. And then, no, I'm just going to get out a calculator. Alright, so if you get out a calculator, do the math, which this problem I guess I was motivated enough to do it for, you get 468.75 minus 166.6 repeating plus 12.5 plus 200, and if you sum those all up, that's 514.583 repeating. But that's c of 50 minus c of 0. So c of 50, the thing we want, is equal to 514.583 bar plus c of 0. C of 0 was $200, so this will be 714.583 repeating. Alright, so that's our cost at 50. Now, I think the other thing we wanted was our cost at, whatchamacallit, for producing between the 21st and 40th unit. Alright, so I'm going to erase this side here, make sure you have that down. Alright. So the cost to produce the 21st through 40th units. In terms of our overall cost function, that's the cost of making 40 of them minus the cost of making the first 20, right? Since we need to start counting at 21. But this is easily expressible by the fundamental theorem of calculus as the integral from 20 to 40 of our original f of x dx, where this is our marginal cost function. Or in other words, this is the integral from 20 to 40 of, I think it was 0.0003 x cubed minus 0.004 x squared plus 0.01 x plus 4. And that we can just straight up compute. This is equal to 0.0003. Yeah, it's the same integration process as earlier, but now we're plugging in 40 and 20. So it's going to be x to the 4th over 4 from 20 to 40 minus 0.004 times x cubed over 3 from 20 to 40 plus 0.01 times x squared over 2 from 20 to 40 plus 4x from 20 to 40. Alright, and if you get out your calculators and do all that, let's see what you will get. Alright, so running just these evaluations through the calculator, you get 0.0003 times 600,000 minus 0.004 times 56,000 plus 0.01 times 1200 plus 4 times 20. Technically, we have parentheses like this, so it would really be 160 minus 80, and that would just straight up give you 80 to begin with. Alright, and now if we simplify these numbers, this will give you, let's see here, 1, 8, and then 10 to the 5th, 10 to the negative 1, 2, 3, 4. So that'd be 180. Minus, let's see, 1, 2, 3, 10 to the 3rd, 10 to the negative 3. So it would be 224 plus 12 plus 80. Alright? And if you add all those together, let's see here. That's 260, 272 minus 224, which is 72 minus 24, which is 52 minus 4, $48. Turns out it only costs you $48 to produce between units 4 and units 20. Or sorry, between units 21 through 40. Only cost you $48. How about that? Alright, so I think that's it for this video. I will see you guys in the next one.